Hi, my name is Josh Wiley. I'm a Senior Research Fellow at Monash University. Today I'm going to be talking about power and statistical analysis plans for clinical trials. You can see an outline of my talk and what I'm going to go over here. I'll begin with some housekeeping and then talk about statistical analysis plans and power analysis for a standard two-arm randomized controlled trial before talking about a newer type of design, sequential multiple assignment randomized trials, or SMART designs. So housekeeping. This talk is formatted in a handout style based on a format commonly used by Edward Tufte. The purpose of this is to have a concise document and actually to be able to have a place where I can write text so that even if you're not watching the video or listening to me, you actually have the information that you need. The other thing that you'll note is different is the use of side notes shown here on the side. Side notes are places for additional details, and they allow me to put in extra references or further information that may not be crucial to the talk or to understanding it, but give you additional useful information if you are interested. The format of this talk is written in R Markdown. R Markdown is a way of writing content in Markdown, which is basically plain text with some very simple markup for headings, etc., as well as having special sections for R code. And I'll use the R code for both the power and the statistical analysis. The results are run and combined into the web page, which is what you're seeing now. But I'll show you what's actually under the hood. Here is an example of this R Markdown file, and this is what actually creates the website. There's a section for title. There's some stuff where I have talk about the style, the side notes, and later on, there are sections that are actually R code. So this is R code, and they're designated by special headings. I use this rather than something like PowerPoint because it allows me to seamlessly combine both text and code and have the output from that code automatically embedded in the website. And the benefit of this is there's no risk of copy and paste errors. This also improves reproducibility, and it's a great format or tool to use for analyses and reports in general. And it's just something I highly recommend for clinical trials, as it allows you to have both the code, the output, and any description or write-up about it all in one place, all reproducible. If you only want to follow along with the ideas and concepts in this talk, you can just watch the video or read this webpage, and I've included the link to the webpage here. However, if you want to run the code yourself more easily, you should actually download the raw Markdown code, which is linked right here. The reason you want to download that code is so that you're not having to copy and paste the code off the website into software. You will also need the data files if you want to follow along. You can get all of those from the talk's GitHub repository, again linked here. Now next I want to talk about just a few tools that I'll be using, and there's really three key tools that I'll use in this talk. First is software for version control. Version control is the idea of keeping a complete edit history of all changes made to files, when those changes were made, and by whom. This history also allows you to undo changes and roll back to a file to any previous version. It's really helpful for clinical trials and research in general, but especially clinical trials where detailed records are valuable. Personally, I use Git and GitHub. GitHub is a central online server that uses the Git version control. And you can find that here. I'll just pop this open so you can see. This link will link to their website. So this is GitHub. I'm signed in already, so you're seeing what I can see, but you'd get to a point where you could sign up. There's free versions, professional versions for academia. And I'm just going to show you one example of using a GitHub repository for a clinical trial that I'm running. So the GitHub repository lists all of the files, and in this case I've made this one public, although you can make them private. I've made this public because these are the power analyses for the trial, and I wanted to be able to show them to the various review committees. The nice thing about it is you can see the commit history. Commits are every time that I said make a record of all the changes made to these files. So if I click on this, you can see the commits that I've made. You can see who made a commit, when it was made. I made a commit on February 8, 2020. That was the most recent change. If you click into that specific commit, I'll just wait for that to load, you can actually see what happened. You can see that I changed 24 files with 2,353 lines added, 2,634 removed. I'm not going to go over all of these, but I'll pop down a little bit later on to some places where there's code. So here's a code file that was actually doing the power analysis, and what you can see here is one line was deleted, line 58 was deleted, you can see what I removed, and in its place you can see what I added. And so commits for text files, which is what a lot of statistical software code basically is, it makes it very easy to see exactly which lines were changed when and by whom, and it allows you to undo that if you need to. That record keeping makes it helpful both for reproducibility and for having audit logs in clinical trials, so something I highly recommend. The other tool that you need is a good text editor if you want to actually follow along with the code I'm doing. The reason for that is you don't want to be trying to copy and paste large amounts of code and text directly into a terminal or console for R. There's two text editors that I recommend. Personally, I use Emacs. It's very old but very flexible. It's free and open source. Another very popular one is RStudio, and both these logos will link you out to where to download them. What I showed you earlier, this is Emacs. There's a list of all the projects that I've been currently working on. I can pop into, there's the code, and there's my R console where I actually run the code and would look at output. The third thing you're going to need is everything in this talk is based on R, which is the actual software and language used for the power analyses and the statistical analyses examples used in this talk. If you're new to R but you want to learn more and you want to be able to set up all the tools, you may find the first few weeks of my Honors Stats class helpful. That's linked here. There's also numerous guides, classes, and books online, many YouTube tutorials, etc. So there's plenty of resources. R is free and open source, works on all major operating systems, so there's no barriers to using this anywhere. If you don't want to learn the code and you just want to follow along conceptually, that's fine too. And when you get to parts of this video where I'm talking more about code, feel free to skip over it till I'm back to a more conceptual content. The first part, and now you can see our code here embedded in this web page, is going to be some setup. So R is a basic platform, but much like using a phone where you might want to install additional apps that give you further functionality, in R you have the basic operating system, the basic software, but you would install additional packages that will extend the functionality. These packages do many different things, and what I'm showing here is a number of them, Tufty, data, table, EM means, etc., that I'm going to be using in the talk today. So this initial part is just making sure that you can load all of the packages that I'll be using in this talk. Again, if you're just interested in this conceptually, you don't need to load these. If you do want to follow along, make sure that all of these can run. If you don't have them installed, you'll need to install them using install.packages. I'll just show that really briefly. So let's say I wanted to get the EM mean packages. I'd type install.packages and then the name of that package, EM means, and hit enter to run that. It'll ask me for the mirror that I want to download this from, and I could pick that and go from there. And there's a little bit of comment next to each one explaining what each package is for, as well as the website for each package when available. Okay, so that's the housekeeping out of the way. So let's talk about standardized randomized controlled trials. To begin with, I'm going to talk a little bit about what I assume you already know. First of all, I'm going to assume that any staff involved in the clinical trial has already gone through basic good clinical practice training. If you haven't, the Society for Behavioral Medicine has NIH-certified GCP training that's free and online. I'm also going to assume that you're familiar with research designs and that you're familiar with basic data analyses, regression, etc. So to begin with, let's talk about a fairly standard two-arm parallel group RCT. And for this example, we'll say that we're going to compare sleep hygiene education to cognitive behavior therapy for insomnia, CBTI. We assume that there's a baseline assessment followed by randomization in a 1-to-1 ratio, that is equal number of people in both groups, the intervention, and a post-intervention assessment that serves as the endpoint. This trial design is diagrammed here in Figure 1. The circle for R indicates when randomization occurs, and the 1:1 indicates that this is happening in a 1-to-1 allocation ratio. Everybody completes baseline, randomized to the two groups, then everyone completes post-intervention assessment. Once you have a trial design determined, my next step is to figure out a statistical analysis plan, or SAP. At the stage of developing a trial proposal or grant, you don't need to write an entire SAP. However, having a clear plan for the core items from Section 6 for the Clinical Trial SAP Guidelines is good. And the reason that I do this, even if I don't have data and I'm not analyzing it yet, and I may not even have the grant, is that having a really clear statistical analysis plan allows me to think about what I need to do for the power analysis, what data I need to collect, whether there are any issues, whether this analysis plan is feasible. If I don't have that clear plan in place, it's hard to work backwards and make sure that all the measures, all of the power analysis, etc., are in place to support that final analysis. So this analysis, this SAP, outlines exactly what the final steps from my trial are going to be. Those last steps when I have the data, I analyze them, and I want to see the results. And from there, I can work backwards to make sure I have everything else that I need. Now, I mentioned these SAP guidelines. If you don't know about it, there's a 2017 consensus paper published in JAMA that outlines what are good guidelines to have in an SAP, what should be there. I'm just going to open that up so you can see this table, because it's really detailed. If you've never written an SAP, or if you have but you didn't really think much about it when you were doing it, or you have thought about it but you just want to make sure that you're following guidelines, these are great guidelines to follow. So they give a lot of information about where they come from, and then they actually have the table. And this is a fairly detailed table. It has a number of different sections. I'm not going to go through each of these, but in an actual statistical analysis plan, after your grant's been funded, if it's for a large clinical trial, you should have an SAP that covers all of these. That would be the gold standard. But I'm going to be focused for this talk on section 6, which is really about the analysis. And the reason that I'm focused there is because I'm assuming that you're not quite at the point of already having your grant funded. So you're writing a grant, you're writing a proposal, you want to do power analysis, you want to come up with a statistical analysis plan, but you're not necessarily going to write a comprehensive 63-item covering detailed plan before you're even funded. And section 6, though, deals with what we really most critically need, for the purposes of this talk at least, which is what exactly is the analysis. What are your outcomes? What are the analysis methods? How are you going to handle missing data? Are there any additional analyses? What software are you going to use? And I've just copied over here the key pieces that we need for this. The outcome definition. This means including all primary and secondary outcomes, how and when they are measured, any planned calculations or transformations. This is important because it determines things like what's the distribution. If we have a primary outcome that's continuous, say sleep duration, but a secondary outcome that's a survival outcome, time until someone develops insomnia or time until someone develops obstructive sleep apnea or something like that, then that's a very different kind of outcome and it will take a very different kind of analysis. So knowing very precisely what the primary and secondary outcomes are, how and when they're measured. If you're going to have any transformations, are you going to apply a transformation? Will it be log transformed, or will you do anything else to it? And that's important for deciding the analysis. Next are the analysis methods. What analysis method will be used? And that's needed for every single outcome. If all your outcomes are basically the same sort of variable, they're all continuous, normally distributed, measured at the same time point only once, then probably you would have the same analysis method for each of them. But if some of them are not normal, some of them are binary, some of them are survival, they're measured at different time points, one of them is a longitudinal one, you'll need different analysis methods for each of those. Whether there's going to be any adjustment for covariates, how you'll check assumptions, alternate methods if the assumptions do not hold. For example, if normality is not met, will you use bootstrapping or some non-parametric method? Any planned sensitivity analyses, any subgroup analyses. Other key points that I think people don't always think about is missing data, expectations around how missing data will be handled. Around missing data, for example, do you think there's going to be a small amount? Do you think there'll be 5%, 10%, 20%, and why? And if there is missing data, how are you going to handle it? Are you only going to analyze the complete cases? Are you going to use multiple imputation? Are you going to use last observation carrying forward? Not a great approach, but often used. So how are you going to handle that? And that becomes important for understanding what the final analysis will look like. If there's any harms or adverse events that are going to be measured, how will they be measured, coded, and are there going to be any planned analyses? Often this is fairly basic, but sometimes more complex analyses are done here, and if that's important, you'd also want to consider that for the analysis plan and for power analyses. And then what software is going to be used. Now, for the sake of this example, I'm going to use a really, really brief goal. So I'm not going to write in this talk a detailed SAP sections even for these categories. I'm going to do something really, really simple, because often in trials it becomes longer and more complicated quickly because people have a primary outcome, but there's also 8 different secondary outcomes and they vary in what they are. And so actually the number of different analyses that are going to be run expands rapidly. But for these purposes, I'm going to show you an example of what I might have written or at least have in my head if I'm writing a proposal, writing a grant, specifically an analysis section. And this may not be written, all of this information may not be written in the grant, but this is information that I will absolutely have crystal clear in my head before I would proceed. Right, let's say here, and this is very simplified, the primary outcome is insomnia severity index, the ISI, assumed to be continuous and normally distributed. This assumption is very important. The primary endpoint is post-intervention. There's no additional outcomes. In reality, almost every grant I see has multiple secondary outcomes, sometimes multiple primary outcomes. But for the purpose of simplicity and ease, we're going to just say there's no additional outcomes. So analysis methods then. Linear regression analysis will be used with condition coded, dummy coded. CBTI is 1, sleep hygiene coded 0, and condition entered as a predictor. Baseline ISI will be a covariate. Assumptions will be assessed graphically via density and scatter plots. Linear regressions with bootstrapping will be used if normality assumptions are not met, and this is considered low risk. I'm going to revisit this when we come back into the power analysis. No planned sensitivity analyses, no planned subgroup analyses. If you did have sensitivity or subgroup analyses planned, and these were critical to the grant, then you need to also consider them when we get to the power analysis section. Both the analysis plan and the power analyses become more complicated. If you don't have them planned, it gets streamlined a little bit. If you do have them, it follows the same approach as you would for the primary outcome. It's just that you have to repeat the steps that I'm going to go through for the primary outcome for each of these sensitivity or subgroup analyses steps. Missing data, again, for simplicity, I'm not really dealing with missing data, so I'm going to say little missing data, less than 5% is expected, and we're going to do a complete case analysis. This is the easiest default way in software. It's often inappropriate in a grant. I don't tend to like to see this unless someone has really strong justification for why they think such small amounts of missing data are going to be used, because we know that oftentimes complete case analyses yield biased results, and there's better statistical methods out there. However, those add additional complexity, and I'm going to make this talk take even longer. Additional analyses, no planned additional analyses. Harms, adverse events, we're just going to do something really basic, frequencies and percentages. Statistical software, we're going to use the latest version of R at the time of analysis. So the planned analysis then could be diagrammed like this in figure 2. The primary outcome and endpoint is post-intervention ISI. We'll have an intercept predicting that, which has a parameter B0, the condition effect, which will predict that, which has a parameter B1, and baseline ISI, which will predict that, which has a parameter B2, and we'll also have the residual variance, the unexplained variability in insomnia symptoms at post-intervention. That's not explained by any of these 3 factors. So this is just a diagram, a sort of way of sketching out what our final intervention primary analysis for the primary outcome and primary endpoint will be. In terms of an equation, we could write our model out like this. We've got our linear predictor part. This is a basic linear regression equation. Eta here is our linear predictor. Intercept, regression slope for condition, which is just the difference between the CBTI and sleep hygiene at post-intervention, and the slope for baseline ISI. And then from that linear regression equation, our assumed distribution is saying that post-intervention insomnia severity symptoms follow a normal distribution, this tilde ends a normal distribution, with mean equal to whatever's predicted for that particular person, eta, and a residual standard deviation, which is the standard deviation of the residuals. And so here for this clinical trial the design that I've laid out here, we've got some sample data. You can download this and read it into R. Or you can just follow along with what I've done here. And here we can see the first few rows of this very simple data set. We've got ID, 1, 2, 3, 4, 5, 6. I don't remember how many people in here, maybe a couple hundred. We've got their baseline insomnia scores, their post-treatment insomnia scores, and which condition, SHE, sleep hygiene education, CBTI. And now we can fit a linear regression model. And in R, we'd use the LM function for linear model. And I'm going to save this and save the results in an object called m.basic. Use a linear regression model, and I'm saying my outcome is post-intervention ISI, and it's regressed on 1 for the intercept, my condition, dummy coded, and baseline ISI symptoms. And the data set is in basic, and that's because I read this data set in and I stored it in an object called basic, because this is a basic RCT. You can use plot model diagnostics to get a graphical assessment of model assumptions. Here you can see a density plot of the residuals with where they all fall, as well as kind of a turned QQ plot. This looks super normally distributed. That makes sense because I made these data up. We can see the predicted versus residual values, scatter plot. We're looking for things like homogeneity of variance here. These look really no clear pattern, so homogeneity of variance likely met. So our assumptions are looking pretty good. Then we can go ahead and look at the results from this regression model. So here, model test, style it for APA. And you get this table here. You can see the estimate for the intercept, asterisk for p-values, 95% confidence interval, estimate for condition CBTI, and this is what we're probably really interested in. This is adjusted for baseline ISI. What is the post-intervention ISI difference in CBTI compared to sleep hygiene education? And here this is saying that CBTI has 3.78 point lower ISI adjusted for baseline. post-intervention than does sleep hygiene. That's statistically significant, triple asterisk, p less than 0.001, and there's our 95% confidence interval. A little bit more information about the model if interested, Cohen's F squared, R squared, adjusted R squared, Cohen's F squared for each of the individual predictors. And we probably would also be interested in the adjusted means for each condition. So not just what's the difference between the groups, but what is the actual adjusted mean ISI at post-intervention. And we can use the EM means function to do that, EM estimated marginal means. So marginal here being that it's marginalizing, averaging over the other predictors, in this case baseline ISI. We want to adjust for that, but we don't want to sort of hold that at a specific point. And here you can see the estimated mean for the sleep hygiene education condition at post-intervention is 20, and the estimated mean for the CBTI condition, 16.3. So CBTI is significantly lower than sleep hygiene education, 3.78 units specifically. Both still high if these were actual ISI scores. You also get the 95% confidence interval for both of those means. Excuse me. So just to summarize this, with the trial design established, the next step is to develop a statistical analysis plan. For a proposal or a grant, I wouldn't write a full SAP just yet, but at least a plan should be in place. You should have in your head what those are. The best practice is to follow established clinical trial SAP guidelines, and I'm just put the reference to this paper as well as a link to it. To my knowledge, there's no specific guidelines for grants, but at minimum, at least when I review clinical trial grants here in Australia, what I look for is what is the primary outcome, what is its distribution, and any calculation that may be done to it, and what is the primary endpoint, post-intervention, change over time, etc. What's the proposed analysis method for the primary outcome and endpoint, and is this appropriate? The appropriate part's obviously critical. Common issues I see surround covariates, failing to adjust for stratification factors, and assumptions I find implausible and that are not justified. For example, if someone says that self-reported sleep efficiency will be normally distributed in a healthy sample, my knowledge of sleep efficiency is that it's not normally distributed in a healthy sample, certainly not when it's self-reported. It may be in your sample, and if someone justified it, that's fine. But if not, and they said we're going to use linear regression and they don't have any backup plan, I'm going to be concerned. So that's where sensitivity or sort of backup analyses, if the assumptions are not met, becomes important. And these are procedures that are recommended for clinical trial SAPs, to have a process in place, a plan in place for when your assumptions are not met. The other thing that comes up a lot for me when reviewing grants on these is how much and what type of missing data are expected and how will these be addressed. For the simplicity in this talk, I just used complete case analysis and pretended there was going to be very low amounts of missing data. In practice, unless I can be reasonably convinced that rates of missing data are likely to be very low, and for me, very low is probably 5% or less or so. There's no strict cutoff on this, but that's around what I tend to take. Complete case analysis is not optimal. Last observation carry forward is also not appropriate. Better methods like estimating equations and statistical models such as full information maximum likelihood or multiple imputation are better. And the highest marks for me would go to proposals that outline both a strong approach to addressing missing data and have planned sensitivity analyses to further explore the sensitivity of results to assumptions about missingness. And I just popped over on the side some articles, including in the New England Journal of Medicine, about best practices for preventing and treating or analyzing missing data in clinical trials and managing missing data in general in analyses. The last thing I want to just pop over is it's really nice. There's a statistical analysis plan for a large trial in sleep from the SAVE study, and that statistical analysis plan is actually viewable online. So I'm just going to open that up now. This actually won an award, I think, for one of the best statistical analysis plans in trials. I don't remember who gave the award, but in any case, the SAVE study was a large study on sleep apnea for cardiovascular endpoints. And this is just an example of the analysis plan. I'm not going to go through all of it, but I just want to highlight a few things about it and the level of detail. Beyond the sort of cover sheet and who's responsible for it, we just look at these table of contents. They have brief introduction and background. You'll see those all fall on one page. Hypotheses and aims, that's important because if you don't know what the hypotheses and aims are, you can't really design an appropriate analysis plan. A handful of pages dedicated to the trial design. And you notice where a lot of these pages go is into what are the study endpoints, primary endpoints, secondary, tertiary, sub-study, safety endpoints, right? So if adverse events or harms, if you have a safety endpoint, what that is. Statistical analysis, general principles, blinding, how they're going to handle missing data, how they're going to monitor adherence, what their baseline comparisons they're going to do, what the analysis population is, its intention to treat, and what exactly that will comprise. Primary outcome, what that measure is, what that analysis is, what subgroup analyses are, adjusted analyses, adherence analyses, how they're going to deal with multiple events. All right, secondary outcome analyses, what all of those are. timelines, and then they have additional things. One of the nice things that they actually do is they have sort of skeletons of tables that they're going to actually report. And the purpose of all of this is both to have this really clearly thought through so that you know that you're collecting the right data and you have a good analysis plan for the clinical trial, and also to prevent people from multiple analyses and doing analyses and sort of finding something significant, or what's sometimes now called p-hacking. Right? So we want to have as much of the analysis for this trial fixed in place so that it really is a confirmatory trial. It's not exploratory work. That's not to say that you can't run all sorts of exploratory analyses on clinical trial data, but that shouldn't be for the primary endpoints. And the statistical analysis plan should outline exactly what's going to be done in as much detail as possible. And what you'll notice here from this footer, this SAP for the SAVE trial is actually 38 pages long. So these are not small documents. They are quite detailed, quite extensive, if done very well. Well, I have a number of different readings and link outs to stuff like for missing data, etc. I don't have further readings on clinical trial statistics. The reasons I don't have further resources or readings for clinical trial statistics is that the statistics used and required vary greatly. They'll depend on the distribution of the outcome and what you assume there, whether the endpoint is a single time point, change over time, whether there's clustering, many more factors. Basically, the statistics for clinical trials is pretty much all of the statistics for any analysis. And so if you're not confident in choosing a reasonable or best approach, if you don't feel like you know what's right, I'd highly encourage you to consult a quantitative expert there. So let's move on now. Let's talk about power analysis. So once you have a statistical analysis plan, an SAP in place, even if it's not fully written, even if it's just sort of those key sections that I talked about outlined in your head, now you can move on and design an appropriate power analysis. It's much easier to design an appropriate power analysis when you know exactly what your actual final analysis is going to look like. The first step is to identify which analyses you intend to power the trial for. Some possible, not exhaustive choices would be the primary analysis for the primary outcome at the primary endpoint, sensitivity analyses for the primary outcome at the primary endpoint, analyses for secondary outcomes, analyses for the primary outcome at the primary endpoint if assumptions are not met, if missing data are high, etc. And what should be clear here is that for anything but the simplest clinical trial, there is not a single power analysis. Rather, there are power analyses, emphasis here on the plural. And you're going to have multiple ones because unless you say, well, I only have one outcome, one endpoint, that's the only thing I'm going to power for, I'm not going to bother looking at power for anything else, you would have to run multiple of these. And even if you have one primary outcome and one primary endpoint, if there's any chance that assumptions may not be met, that you have a lot of missing data, etc., and you might have some sensitivity analyses, you may want to look at what the power would be like for those sensitivity analyses, or if those assumptions are not met. Is that going to ruin your whole trial and you will no longer be adequately powered at that point, or would you still be okay? There's a lot of tools and many approaches to power analyses, but a common proposal or grand approach I see goes like this, or at least this is what people would say if they were sort of overly honest. We're going to do some fancy analysis, but we based our power analysis off some different crude approximation that may be relevant. In practice, it looks something like this. Planned analyses are linear mixed models. Power was based off of Cohen's d at post-test, which should be conservative. Probably many of us are guilty of this. I'm certainly guilty of doing something like this before, but this workshop's about being better, doing clinical trials the strong way. So rather than talk about crude approximate power analyses, ways that you can take sophisticated analyses and do a power analysis that may be sort of hopefully close enough, I'm going to talk about an approach that can be very robust. And the problem is, well, there's a lot of rules of thumb for power. There's a lot of pre-built software, approximate equations, lookup tables, and more. There's many, many different statistical models that can be used. And you would need separate equations or software or lookup tables, etc., for each of those. And easy tools that cover the myriad of possible analyses for clinical trials do not exist. And so you see those crude approximations that I mentioned above. So the question is then, well, what's the alternative? Is there a unified, is there a better way? And the answer to that is actually yes. There is a general approach that's flexible and covers many different settings that is actually also very high quality. And that approach is called Monte Carlo studies or Monte Carlo simulations. They can be used to provide accurate power analyses for basically any statistical analysis plan. The catch here is that it takes time and it takes some work. It takes some familiarity with statistics, with your model, and with some sort of coding. Here, I'm going to show you the basics of a Monte Carlo study to power our standard 2-arm RCT that we already developed the SAP for. Now, the core behind Monte Carlo studies or Monte Carlo simulations, those are interchangeable words, involve repeated random sampling to generate a range of plausible scenarios, in this case, a range of plausible data sets, and then analyzing these random data and synthesizing the results. Monte Carlo studies get used for a lot of things, but in our case, we are going to be analyzing and then synthesizing the results to determine the sample size needed for our clinical trial. To start off a Monte Carlo study, we need a crystal clear idea of what our statistical analysis actually is, and what all the data are going to be. So we're going to start with that analysis diagram for our primary statistical analysis, but with a few additions, and I'm showing this here in figure 4. You'll notice that we've got the intercept, baseline ISI, condition, and post-ISI as we had before, but there's some additional paths added here. There's some new paths, there's some additional pieces. The intercept for the baseline ISI. With no predictors, the intercept is going to be the mean. So that's basically saying what is the average ISI at baseline? What is the variance of ISI at baseline? Another is what is the probability, the intercept to condition here. That's what's the probability of being in a given condition. This one we should know because we randomize people and we know our allocation ratio. So we should know there's a 50-50 chance of being in each condition, or if you're randomizing 3 to 1, there's a 75 or 25 probability of being in each condition. Another is what is the association between the condition and baseline ISI. In this case, we don't have to worry about that because we randomize conditions, so we're going to assume that the association between the two is 0. But we do need the average ISI at baseline, the variance of the baseline ISI, the probability of being in a given condition, and estimates for what the intercept of the post-ISI is, the difference between CBTI and sleep hygiene at post-ISI, and the relationship between baseline ISI and post-ISI, as well as how much unexplained variability there is at post-intervention ISI. So for a Monte Carlo study, to actually do this, to generate random data that we can analyze for our clinical trial, we need to fill in basically values for every one of these paths that I've outlined here, as well as make some distributional assumptions. So we're going to assume that both baseline and post-intervention ISI follow a normal distribution, conditions binary, 0, 1. We set that up, so that's fine. Here I just talked about what each of those values are. Right? B0 is the intercept of post-ISI. B1 is the adjusted difference between in post-ISI between CBTI and sleep hygiene. B2 is the slope, the regression slope between baseline ISI and post-ISI. This is basically stability. How much is where people's insomnia symptoms started related to where their insomnia symptoms ended up? How strongly are they related? If that's 0, that's saying they're completely unrelated. If it's very high, that would say they're very strongly related. Variance of each. B base is the intercept or the mean baseline ISI. Association between condition and baseline ISI, we're going to assume that's 0 because we randomized condition. And the probability of being in condition 1, CBTI, we have a 1-to-1 allocation ratio, so that's going to be fixed at 0.5. But for everything that we can't fix because we're not allocating it or we haven't randomized it, so we assume no association, we actually have to plug in values. We need to plug in values for every one of these parameters in order to do a Monte Carlo study. Now, these parameters are all very easy to estimate if data are available. They're things like standard deviations, variances, mean, a regression slope. But without data, it gets a little bit more challenging to derive each of these from the literature. And here's just an example of how this process might look. I work in cancer, so I'll use that as an example. Suppose I'm going to do this RCT, this one that we talked about here, and I'm doing it for people with colon cancer right after diagnosis, and it's going to run for 1 month. The first thing I'd try to look for, if I didn't have any pilot data to base this off of, would be to look in the general literature to find observational studies reporting ISI in people with colon cancer near diagnosis, ideally at exactly the same point at diagnosis that I'm going to be recruiting them into my intervention. But I'd take as close as I can get. And from those studies, I can likely get the mean and standard deviation of ISI, which will give me my values for the B base and the baseline ISI variance. Okay? That's going to give me these parts, basically. What is the distribution of this thing? I'm assuming it's normally distributed. That may not be true, but if that wasn't, I might need to alter that distribution assumption as well. Next, I'd go looking for any longitudinal studies, and I'd use those to try to estimate what is the stability of ISI over time. If my intervention is 1 month, so my baseline and post-intervention are about 1 month apart, I'd ideally find a longitudinal study that reported what the stability of ISI was in people with colon cancer right at diagnosis over a 1 month period. If I could find all of that, that's perfect, and I'd use those estimates. If not, I try to find different studies. Perhaps I find a study that has an 8-week and a 12-week follow-up, that is a 2- and 3-month follow-up, and I might see how different those results are to get a sense of whether the stability of ISI in colon cancer varies a lot or it's relatively stable. If it's relatively stable, there's not a lot of differences over time, then I might just plug in those stability estimates from 8 or 12 weeks into my 1 month. If it's varying a lot, then I'm going to be a little bit more nervous because I'm going to say I can't actually get a very accurate estimate. There's a lot of uncertainty in my estimate of what the stability of the ISI is. Even if I can find something, it's likely to be a correlation, which I'll still need to convert to an unstandardized regression slope to plug into my Monte Carlo model. Next, I need to consider what change in ISI I'd expect in the control condition, that is sleep hygiene. Right, that's going to give me my post-intervention intercept. So people start at 14, even without, in my control condition, say sleep hygiene, how much are they going to go down? I base this off of a couple of things, because this is going to be a combination of sleep hygiene effects, but also any naturalistic change that occurs over time. So I might look for observational longitudinal studies of ISI in colon cancer to see if I can get an estimate of the naturalistic change. Is it fairly stable? Is it going up? Is it going down? And by about how much? And then look at any intervention studies that have utilized sleep hygiene to say, well, what's the effect of sleep hygiene? Is that, and try to get an estimate of that. And I'd combine that with what I thought the naturalistic change was going to be, and together use that to say what that estimate is. Fourth, I'd consider what difference I expect or wish to have adequate power to identify between sleep hygiene and CBTI. This may be based on previous trials of CBTI, meta-analyses, minimally important differences on ISI, etc. This needs to be in the ISI units, since ISI is my primary outcome. If you have a different primary outcome, it needs to be in whatever the units of that primary outcome are. For example, I may say that a 4-point change in ISI is the smallest effect that I am interested in being able to detect. This is not a standardized effect size. And a lot of people lean on standardized effect sizes for power analyses as they simplify life, but they are fundamentally a ratio of the absolute raw effect to the amount of variability. And I don't think this is really ideal to rely solely on that. They're helpful to aid our interpretation, but when we're thinking about what we actually care about, I don't think most people would sit down and say, well, I care about a Cohen's d of 0.3. For example, clinically, would I care less about a 4-point decline in ISI if the between-person standard deviation of post-ISI was 6 than if it was 2? If people decline 4 points, do I care how much variability there is between my participants? Right? And I might say, well, in both cases, I think that a 4-point decline has the same value. The power is going to be very different. The standardized effect size is going to be a lot smaller if there's a 6-point standard deviation than if there's a 2-point standard deviation. However, if I think that a 4-point change is meaningful, I'm likely to think that that's meaningful regardless of how much sort of background noise there is. So the absolute intervention effect can remain the same, even if the standardized effect can change. And you may say you only care about the standardized effect, and that's fine, but I think working with absolute values forces you to be explicit about the two parts that go into a standardized effect. A, what do you think the absolute difference is? B, how much variability do you think there is? So rather than just having a single ratio that you sort of estimate, it actually forces you to think about each part of that ratio. So fifth, I try to estimate what the residual variance of ISI is at post-intervention. Unless I'm expecting a very large intervention effect or a lot of change over time, one way that I often start with this is that I might assume that the post-intervention ISI standard deviation is pretty similar to baseline. The residual will be smaller because a lot of the variance should be explained by baseline ISI, assuming that those are correlated over time. But I'll sort of say, well, if I wasn't controlling for baseline, I might assume that the standard deviation is about stable over time. That doesn't always pan out, and again, lean on literature, try to find estimates to fill this in. If you have actual data, that's the easiest. At this point, some sort of estimates exist for all the parameters that are needed. The last thing that I try to do in this case is think about where may I be wrong. For example, am I very confident in the slope of post-ISI on baseline ISI, that is the stability of ISI over time? Was that based on limited or poor data? If I had to use data from a study of 20 men with prostate cancer rather than a large sample of people with colon cancer, I may be less confident that my estimate is the truth, or even a good approximation. If I'm not very confident in an estimate for a particular parameter, then what you can try to do is to try to choose a range of values, kind of a lower and an upper bound, or a most plausible and a conservative estimate. Right? Try to choose a range of values that cover a plausible spread for that parameter. Once we have all these parameter estimates, it's actually fairly easy to code a Monte Carlo simulation study. It does take some coding. You do need to know some software to do this, but the steps are fairly simple if sometimes it gets tedious or longer if you have more complex settings. Conceptually, there's just a few steps. for every set of parameters, for every parameter set that I've laid out here, right? If I knew the exact truth, I would just have one set. But if I'm uncertain, I'm like, better try a 2 and a 3 here because I'm not exactly sure how much change there's going to be. Or better try a 1 and a 6 for the residual variance because I don't know exactly what it is and I think it's going to be bounded somewhere between 1 and 6. Then that starts to create different possible sets of these parameters. So for every one of those, generate k, that's some number of simulated data sets with n participants. Once, that might be 100 participants. Another time, that might be 200 participants. On each of those k data sets, conduct the planned analysis and record the p-value, in this case for the condition effect. Record the p-value for the difference between CBTI and sleep hygiene. And then we just calculate the proportion, the mean, of p-values that are less than alpha. Often our alpha is 0.05, but whatever you want to be, across all k data sets. And this is the empirical power for n participants and that set of parameters. So what Monte Carlo studies let us do is say, under the conditions that we're assuming, with the parameters that we're assuming, we can generate a data set, and then we can actually conduct our final planned analysis on that data set and look at the p-value. And we do that over and over and over with different random data sets, and that will show you the statistical power empirically for that particular set of conditions. Then we just vary the number of participants, 100, 110, 120, 130, 140, 150, etc. And from that, we can figure out, well, how many participants do I need to achieve whatever power level I desire? Often 80%, but it doesn't have to be. Now, Monte Carlo studies involve random samples, therefore you may get slightly different results from one time to the next. To minimize this, you can increase the number of random samples. You can increase k, generated for each combination of parameters and sample size. And this is great because it reduces the variability, gives you a more precise estimate. The only downside is this requires more computer time. If it's really quick, that may not be an issue. If it takes a really long time, you may need to watch that. So in the code that I'm going to show you, I made the following choices. I varied the sample size from 100 to 500. If you find that even with 500 people, you only have 20% power or something, you may need to increase that a lot. Or if you find that with 100 people, you already have 100% power, you might look lower, like 20 to 100. This is just sort of what I began with as a, I think it's hopefully going to be somewhere in this range. That might also be based on what I actually think I can feasibly recruit. If I know there's no way I can recruit more than 500 people, then there's no point at looking at what power would be above that because it's impossible to do anyway. Probability for condition is 0.5, that is, it's 50% chance of being in each condition. The mean ISI at baseline is 14. The standard deviation of ISI at baseline is 5. The post-ISI intervention, post-ISI intercept in sleep hygiene is either -1 or -2. The adjusted difference between sleep hygiene and CBTI at post is -4, -3, or -2. So here I'm examining a range of possible parameter values. I don't know exactly how much impact CBTI is going to have relative to sleep hygiene, and I want to evaluate it. What if it's a 4-point, 3-point, or 2-point difference? The post-ISI residual standard deviation is 4. The stability of ISI over time, that regression slope, is 0.5. Next, we create all possible combinations of these parameters, and that gives us 126 total different combinations. Most of those, we get 6 here because of these two parameters, but the rest of them come because we're varying the sample size. Then we have to decide for every combination how many random data sets do we want to generate. The more we generate, the more reliable the results, also the more time-consuming computationally. Here, I'm going to choose 200 different random data sets for every combination. So we have 126 combinations. Each one of those will have 200 random data sets generated. And that gives us a total of 25,200 data sets in total. Those will get randomly generated. We'll run our linear regression model on each one, and we'll extract the p-values and store those. This next part is heavy on our code. If you only care about this talk conceptually, you just want to understand power analysis, statistical analyses plans, and a little bit about Monte Carlo power, then feel free to skip this part of the web page and the next part of the video. For those who are interested, I'm going to spend a little bit of time talking through what this code is doing. You may not be super familiar with it, but hopefully with a bit of a walkthrough, you'd at least be able to understand how you might tweak it. So what I'm doing here, I'm going to store all these different parameter combinations in an object called params. That's going to be a data table. Expand.grid is a function to say, give me all possible combination of the next set of parameters that follow. And those parameters are as follows. N is going to be a parameter. It's going to be a sequence from 100 to 500 by 20. Probability, I'm saying, is going to be set at 0.5. My B base, which is that mean of ISI at baseline, is going to be set at 14. Baseline ISI standard deviation, set at 5. B0, which is my post-intervention intercept, is going to be either C concatenates multiple numbers together, so it makes a vector. So it's going to be either -1 or -2. My CBTI effect B1 is going to be -4 or -3 or -2. My post-ISI standard deviation is 4. And the stability of ISI over time is 0.5. And that will all get put together into a data table. The head function shows just the first 6 rows of that data table. And so you can see what this likes. This is basically a data set itself, where this data set contains all of the different conditions I want to evaluate. So here you can see that most of my parameters are staying fixed, but the sample size is changing. If we went on to later rows, you would see these other parameters that I had chosen also coming into effect. So this is a data set that lists all the different combinations of sample size and parameter values that I want to look at. Next, I want to decide how many replications I want to do for each condition. And this code is a little bit complicated, but the key part here is this 200, which basically says replicate this parameter data set 200 times. And again, overwrite that in parameters. And then I create one more variable in this data set called run, which is just a number, a sequential number, basically the row number, from 1 to the number of rows in this data set. So the first row is 1, 1, the second row is 1, 2, etc. And that gives us that 25,200 different rows in this parameter data set. And that's how many times we're going to generate random data. Now, I've already run this, and so I've set this if condition to false. So I was saying if false, meaning don't actually run this code. So I'm telling R not to run it again. It takes some time, and I've already run it and stored the results. If you want to run it yourself, though, you could just set this to true and go in. To speed things up, I'm using a local cluster. This will help me take advantage of multiple cores on my computer. I'm using 24 cores here. If your computer doesn't have 24 or more cores, you want to set this to the maximum number of cores you have or something lower. Then on this cluster, which is called CL, I'm loading the packages. Cluster eval q lets me run specific code on that cluster. So I'm loading the specific packages I need just for this Monte Carlo. It's not all the packages I'm using in this talk. It's just the ones I need to generate these Monte Carlo data sets. So data table and EM means here. Then I need to export my data set, my parameter data set, to the cluster, done here. Register that I want to use the cluster for parallel computations. I use set.seed, and I just made up 1, 2, 3, 4. You can plug in any number you want here. This helps make sure that if I run this and then tomorrow I run this code again, I would actually get the same results. So even though every data set has different random numbers in it, I can make sure that the computer gives me the same random numbers every time by fixing the random number seed here. And then I'm going to store all of the results in this object, basic Monte Carlo results. I'm going to combine them all together by Irvine. I'm going to use for each, which is basically a for loop. It's going to say, go have the computer do it for I equals 1, then I equals 2, then 3, then 4, then 5, then 6, all the way up to the number of rows in my big parameters data set. That's 25,200. And combine those all together. This do random number generator operator here, %do_rng, this is going to be a parallel for loop, but I'm saying that even though I'm running this in parallel, it's random numbers are being generated, and this will help make sure it's reproducible. And so this is just all sort of the setup to run in parallel to do this same computation. Everything that comes after this little bracket is going to be done 25,200 times by the computer. So the same code is going to get repeated over and over and over again with different random numbers each time. So the first start is I'm going to create this sort of basic simulation data set. It's a data set. I'm going to say, give me condition where you sample 0 and 1. And I want to sample each 0 and 1. That's my two conditions, sleep hygiene and CBTI. The number of observations times the probability of being in each condition. Baseline ISI should be a random normal distribution or norm. And I want to generate n observations. The mean should be the baseline mean. The standard deviation should be the baseline standard deviation. Next up, I need to generate the post-ISI values. So now I'm going to say post-ISI values. Those are also random normal distribution. I also want n random normal values. And that mean is going to be the mean, my intercept, plus my intervention effect times which condition they're in. Remember, I've already generated zeros and ones for the condition, plus the slope times the baseline ISI values. I've already generated random baseline ISI values that have the mean and standard deviation that I wanted. And the standard deviation of this random normal values should be the post-ISI standard deviation. And so now this bit of code here, this has generated my baseline ISI, my condition, and my post-ISI. Next up, just a little bit of tidying. Right now, my condition has names 0 and 1, so I use this factor thing to say label. Those levels 0 and 1 should actually be labeled sleep hygiene education and CBTI. That's purely for aesthetics. Now I run my linear regression, LM, and this is now using this simulated data that are these random normal values that I've just generated here with these parameters, which I specified up here, that big list of 25,000 different ones. N will be varying. We'll take the ith n, the ith intercept, etc. That's what that little bracket I stands for. And I'll store that linear regression results in msim.basic. And then here comes my output. I'm just going to indicate what run it is, run I, so that'll first be 1, then it'll be run 2, then run 3, then run 4, all the way to 25,200. And for the p-value, I extract, using this little bit complicated code, I get a summary of my linear regression model, get the coefficient table, and because I've looked at this before, I know that the condition effect comes on row 2, and I want the p-value column, which is labeled this, so I just put that in. And so this gives me a data set that will have which run it was, 1, 2, 3, 4, 5, etc., and a p-value. This is run in parallel, and then I merge those p-values back in with my parameters data set. That way I know what p-value belongs to what particular set of parameters, and I do that here using merge. And then I save these results so that I don't have to run it every time and shut my cluster down. On my computer, this ran, I think, about 30 seconds to run. That's using 24 cores. This should scale fairly linearly with the number of cores. So if you were doing this on a single CPU core, it'd probably take around 12 minutes. It would be a very rough approximation. Just to give you sort of an estimate if you're trying to run this on your own computer. If you want to run it yourself and you don't want it to take as long, you could reduce the number of n here that you try, or rather than doing 200 data sets for every condition, you might choose just 20 or even 2 if you're just trying to run it to make sure the code works and test things out for yourself. So I saved those results. If you want to download the data set so you can run what I do next here, you can download it right here. All right, so now we can graph the results, which are shown in figure 5. And if you are just following along conceptually and you don't care about code, you should start paying attention again. Because graphing the results is actually showing us, well, what are the Monte Carlo simulation study results for my power? So this key part is here. This is just code to actually do the graphing. The only conceptual piece that's relevant here is the way we actually calculate the power empirically. We take the p-values we observe from all those different data sets, and we look at whether they are less than 0.05 or not. And if they are, then that gets a 1. It's significant. If they're not, it gets a 0. And we look at what that average is. So this plot here, and it's made with this code. If you don't care about the code, ignore it. If you care about the code, you can copy it. Shows on the x-axis here is the sample size. On the y-axis is the empirical power. The different colors and lines is the difference between CBTI and sleep hygiene education at post-intervention. And the different rows are, what was the other parameter we varied? The different rows are the intercept at post-intervention. Right? So is it -2 or -1? And that has to do with basically how much, what mean you expect in the sleep hygiene education condition. And we can see from the graph is that the two different rows, this -2 and this -1, they look pretty much the same. So actually, the change over time in the sleep hygiene condition doesn't matter so much as the difference between sleep hygiene and CBTI matters in terms of power for this p-value that we're focused on right now. And what you can see is that if there's a 2-point difference, then you can see the power as n varies from 100 to 500. If there's a 3-point difference, you can see it. If there's a 4-point difference, you've got that solid purple line. And I put a horizontal line here at 80% power, which is a typical power desired for clinical trials. Sometimes people go 85, 90%, but 80% is certainly the most common. And then I put a vertical line right around the sample size needed, and I think I put that at 140, which is if you had 140 participants, 70 in each arm, that would give you 80% power even for our smallest 2-point difference between CBTI and sleep hygiene education at post-intervention. And so what this is now showing us, what we can see here, is actually these power curves for these different scenarios being evaluated. So this is really the key from our Monte Carlo study. Now, in proposals and especially for grants, you can't present this much detail. However, you can briefly describe a Monte Carlo study for power, where the estimates came from, etc. When I do them, I like to evaluate a range of plausible conditions. This doesn't guarantee that any of my conditions, any of the parameters I plugged in are true, but at least I haven't put sort of all of my eggs in one basket. I didn't just come up with one set of parameter estimates that the best I think I can come up with, and I hope that I'm right. I'm able to look at least some variation around those parameters. If I think that 3 is the best estimate, I might try 2 and 4 just to see how much does that influence my results. If my results showed that 140 people provided sufficient power only under the most optimistic scenarios, I'm going to be worried about my trial. I'm going to be worried that one of my, the scenario is not actually true, and then I'm going to end up underpowered, and I'm going to end up, even if I find the result, the magnitude of difference I expected, that I'm not going to have power to say that's actually a reliable difference. In text, I include graphs if possible, and if not, I briefly describe the study along with something like, in 22 of the 28 different scenarios examined, X number of people provided greater than 80% power. This sort of way is how I would tend to sort of shorthand summarize it. And what I'm trying to convey is that I actually carefully thought about many different scenarios. I evaluated a lot of them. Under most of them, this is a reasonable approach. This is an adequate sample size for many conditions, right, that I believe and I can argue are plausible. I've drawn those plausible scenarios from literature, from pilot data, wherever I got it. The challenges of Monte Carlo studies are typically, one, identifying plausible parameter values to use. This can be quite time-consuming. You have to dig into the literature. People don't always report exactly what you need, and it really makes the case that it's sometimes very, very helpful to have pilot data. And the other part that can be challenging is implementing that conceptual model into code. Although identifying these parameters takes time, I find the process is really valuable and it strengthens clinical trials. It forces either pilot data or extensive literature search and becoming closely familiar and making very explicit assumptions about what data you expect to collect during the trial. The assumptions may be wrong, but they're equally present if you do a simpler power analysis based off standardized effect sizes or some sort of cut and dry rule of thumb or formulas. And in the Monte Carlo study, you make those assumptions very explicit and you're forced to grapple with those choices and you're forced to think about them. How much variability do I expect? If that's much larger, if I think my intervention can reduce ISI by 4 points, but when I look into the colon cancer literature, I find that there's huge variability in sleep and the standard deviation is 12, while in insomnia, the standard deviation is normally 4. Even if I think my intervention can reduce ISI by 4 points, I'm going to realize now I'm going to be drowned in all of this background noise. What am I going to do about that? And so this process of actually picking all these parameters really forces you to think very carefully about what sort of data you ultimately expect and why. Another benefit of the Monte Carlo studies is that you literally have synthetic trial data sets. These data sets should look exactly like the ultimate trial data that you're going to analyze. This means before you ever collect any real data, you can have functioning code to conduct your analyses. Having code for analyses forces them to be explicit. You can't just say, oh, we're going to have some covariates, or I'll run a linear mixed model. I don't know how to do that. I don't know exactly how to code that, what's going to be random effects or not. You have to actually code it all out, and that forces all of that to be explicit. And you can make sure that it works on these synthetic Monte Carlo data sets. And this can be part of the trial pre-registration so that actual functional analysis code is registered. Side note, benefit of Monte Carlo studies, if you want to use a different value, it's really easy to change. Up here, where I had in this code p-value less than 0.05, I could plug in p-value less than 0.01 or anything else that I wanted, and then I would get power based on that new alpha. Every Monte Carlo study is going to look different as they depend on the assumptions and the planned type of analysis. But here are some articles that are focused on giving tutorials to Monte Carlo studies. So these are just a few different articles that should sort of help you get familiar with this if you want to do something like this. All right, so last up, I'm going to talk about sequential multiple assignment randomized trials, or SMART trials. I started with a standard simple 2-arm trial design as it's easier to follow. Probably most of us are familiar with the design, and using that simpler design, I can talk about the SAPs and the power analyses. But the real benefits of Monte Carlo studies are when you've got power for more complex designs and more complex types of analyses for which there don't exist any good, easier ways to calculate power. If you simply have two groups and a mean difference between the two groups, t-test power exists and there's software for it and it's easy, quick, and fine. But the Monte Carlo approach becomes very powerful and flexible when you have more complicated trial designs, more complicated analyses for which power is not readily available. Because Monte Carlo studies can calculate power for basically anything. As long as you can describe the distributions and the relationships between all of your variables, and as long as there exists an analysis for that data, which there needs to be if you're actually planning to do a trial, then you can run that analysis on your randomly generated data, and that will calculate empirical power. It will work for anything. So we're going to consider now these SMART trial designs. SMARTs involve more than one point of re-randomization, or more than one point of randomization, I should say, not re-randomization, and they're particularly good for testing adaptive interventions. We're going to work with this SMART shown here in Figure 1. I'm not showing the assessments here, but assume that there's a baseline assessment, then people are randomized in a 1-to-1 ratio to either self-help light therapy or self-help CBTI, and then they get that intervention, that self-help intervention of either light or CBTI for 1 month. After that 1 month, they're measured again on the ISI, and they're classified as either having a response to the intervention or no response. And here, arbitrarily, I'm going to pick a 4-point decline as my threshold for response. So if they decline by 4 points on the ISI, then they're considered to have responded to the intervention. If they have declined less than 4 points, or hopefully not, but increased in ISI, then they're considered not having responded. If they respond, then regardless of whether they're allocated initially to self-help light or self-help CBTI, they continue with that self-help condition they were in. Right? Here's condition 1 and 4. If they did not respond, then they are re-randomized in a 1-to-1 ratio to either a more intense version of the same thing. For self-help CBTI, that's therapist-delivered CBTI. For self-help light, that's still the same light, but then augmented with, let's say, problem-solving and motivational interviewing to try to help people to regularly use that light. The assumption is the light works. You don't need to make the light brighter because you've hopefully already done a bright enough light, but maybe you need to get people to use it more. Or the other thing they're randomized to is the other intervention. So if they're randomized initially to self-help CBTI, then they might get later on randomized if they don't respond to that to add self-help light in addition to self-help CBTI. Or if they were initially randomized to self-help light and they didn't respond, they might get randomized to add self-help CBTI on top of the self-help light for another month. And then here at the end, not shown in this diagram, would be the post-intervention final assessment, again, 1 month later. So baseline, 1 month of self-help treatment, evaluate whether they respond or not with another measure of the ISI at midpoint, another randomization for some people, not everyone, and then measure 1 month later post-intervention. And this trial essentially is comparing the use of light therapy or CBTI, but in both cases the interventions are adaptive. And this sort of describes what I laid out here. Now, this SMART trial follows a fairly typical stepped care type model. Non-responders get a more potent dose, but it can answer multiple research questions. And these are just a few. This isn't an exhaustive list, but it gives some examples. Given the second stage interventions, the people randomized to self-help light or CBTI have better outcomes. That is, just evaluating the stage 1 randomization. So given what happens next after that, all the different possibilities, just starting here or starting here, overall, these outcomes, which one ends up better? And that's basically kind of averaging conditions 1, 2, and 3 versus 4, 5, and 6. Another more nuanced question, if people do not respond to their stage 1 intervention, is it better to intensify / offer more support for the same type of intervention or add a self-help but different intervention? And that would be basically comparing intensifying, which is sort of groups 2 and 5, to the switch intervention type, add another type, groups 3 and 6. More specifically, you can also ask, is the adaptive intervention that starts with self-help CBTI and continues with that for responders, but offers therapist-delivered CBTI to non-responders, superior to the adaptive intervention that starts with self-help CBTI and continues with that for responders, but offers self-help light to non-responders? So this is a now much more specific question comparing two different possible adaptive intervention programs, right? Start with self-help. If they respond, continue. If they don't respond, give them therapist-delivered CBTI. Start with self-help. If they respond, continue. If they don't respond, add light. Right? Which of those two is a better overall adaptive intervention program? Notice here we're not just comparing two specific outcomes. We're not just comparing in the non-responders these outcomes. It's actually that whole adaptive intervention. Which of those two potential kind of stepped care type models is actually better, or are they different? And that's a possible question we could answer. There's more questions that could be answered because there's other adaptive interventions nested in here with light, and we could make comparisons between with light or between starting with light and adaptive interventions that start with CBTI, etc. So these smarts are nice that they allow multiple questions to be addressed in a single trial, oftentimes many more than just a 2-arm trial allows, and they're especially good for evaluating adaptive intervention stepped care type models and trying to figure out which of multiple possible stepped care models is actually optimal. Now, it's going to be a challenge to find any fixed software to calculate accurate power estimates for this kind of smart design. And even if the outcome were continuous, normally distributed at a single time point, let alone if this whole smart is happening in the context of clusters of people nested within therapists or sites, had repeated measures endpoint or survival endpoint, etc. Some tools exist, but it starts to get very limiting, and you start having to make a lot of approximations that may not be very good. If using a SMART in a proposal or grant, it's also going to be likely helpful to include some general description and a really clear write-up, as I would not expect most reviewers to be familiar with them or to have only limited knowledge. Plan to keep extra space in your proposal or grant for that purpose. The next sections I'm going to show you how we could analyze this SMART, and then once we have that analysis down, we'll be able to talk about a power analysis. Because again, it's very hard to do these Monte Carlo studies if you don't have analysis, but if you've got a crystal clear analysis in place, then we just have to simulate some data, apply that analysis to it, store the p-values, and make our graph. One of the primary papers, perhaps the primary paper on how to analyze SMARTs, is this one shown here in Psychological Methods. It's a few years old now, out of Susan Murphy's group, as the sort of lead senior author, but many other people that she worked with. This is strongly recommended reading for anyone if you're proposing or analyzing your own SMART trial. I really recommend it. It's quite a, actually it's behind a paywall, but it's quite a readable paper. It is a methods paper. There's some parts that might be tough, but a lot of it will be followable, I think, even if you don't have a strong methods background. An example data set for this SMART trial is available from my GitHub repo, or you can download it right here. And so we can read the data set in, and then we'll look at the first few rows. So here, excuse me, I read that SMART data set in, and just look at the first 6 rows here in Table 4. You've got ID, you've got their baseline ISI, you've got their midpoint ISI. We're using that to determine whether they had a response or had no response. Post-intervention ISI, whether they had a response or not, coded 0 or 1, 1 if they had a response, i.e. a 4-point decline from baseline to midpoint, or 0 if they didn't, less than a 4-point decline or an increase. Which intervention they were randomized to at stage 1, CBTI or light, and at stage 2, which intervention they were randomized to. Now, if people responded, they continue on with what they were, so they're not re-randomized, so they're just NA, not available, missing. Otherwise, it's coded as either higher intensity or both interventions. And higher intensity is actually here groups 2 and 5, and both interventions is groups 3 and 6. That's at stage 2. You can either sort of get a more intense version of whatever you got in stage 1, or you can switch and get the other version that you didn't get at stage 1. So that's our basic data set. Table 5, coming up down here, shows basic descriptive statistics by the first stage intervention. So here you've got the mean and standard deviation for baseline, mid, and post ISI in the people randomized to the light at stage 1 or CBTI at stage 1. And you've got the number and the percentage that did not have a response and that had a response in each condition. And this response is probably the most useful thing, because one of the things about SMARTs that impacts power is if you're focused on looking at that second stage randomization, if you have something where only people who do not have a response get re-randomized, then you're going to be working with these people here. So even though we started with 120 people in each condition, only 90 people in the light condition, 75%, did not have a response and therefore get re-randomized. 86 people in the CBTI condition did not have a response and therefore got re-randomized. The rest of them had a response, so they're not re-randomized. So they're not going to feed into that re-randomization part of the trial. If these numbers were really different, if 90% of people had a response, you'd only have 10% of people getting re-randomized. That'll change your results a lot. So that becomes pretty important in these. One way we could evaluate the stage 1 intervention main effects in the context of the stage 2 interventions is simply ignore stage 2. Right? We could just run a regression that only compares whether you initially randomized to self-help light or CBTI. It doesn't look at anything that comes after that. It just says, well, depending on which one do you start, does that make a difference? Control baseline ISI, look at post-ISI. This is a standard regression model. Nothing special you have to do here. And we can see that the people randomized to self-help CBTI initially do 0.73 points lower on this ISI at post than those initially randomized to self-help light. Not statistically significant, but sort of the direction is maybe slightly better for self-help CBTI. Not a huge effect, though. If we want to compare the adaptive intervention programs, it requires a few more issues to be addressed. And I'll go through those very briefly. All of these are actually discussed in a lot more depth in that paper I mentioned. So if you need more details, you want to find out more, this is sort of your reference point. The first issue is that participants don't have an equal probability of being allocated to each group. is people who do not respond are subsequently allocated to one of two groups. Right? So if you respond, then you can get allocated to CBTI, and you've got a 50% chance of that happening, but you only have a 25% chance of getting allocated to one of the subsequent groups. We can solve this to achieve balance by weighting the data. So people have a 0.5 probability, people who respond have a 0.5 probability, whereas people who don't respond have a 0.5 times 0.5 or 0.25 probability. We use the inverse of that, i.e. 2 and 4, as weights in the data set. We'll use those weights in the analysis. So here I'm just adding a variable weight to the data set, which says if response is 1, if people responded, then give them a weight of 2, 1 over 0.5. If not, give them a weight of 4. If you had a different allocation ratio, if you didn't use 1-to-1 allocation, if you use 1-to-2 or something like that, you'd have to adjust the probabilities and adjust the weights. But it's pretty easy. Just take the ratio. The other issue is that if we want one analysis to compare all adaptive interventions, we need to count responders into each adaptive intervention. The reason for this is an adaptive intervention isn't only what happens if they don't respond. The adaptive intervention is you start off with self-help CBTI. If they respond, you continue with that. If they don't respond, you increase the dose by giving them therapist delivered into CBTI. Or you start off with CBTI. If they respond, you continue with that. If they don't respond, you add light. That is the entire stepped care intervention. Right? So that whole program includes both the non-responders and the responders. So to evaluate each program as a whole, we need to include responders in each of it, but we only have one set of responders. That turns out to be pretty easy. We just duplicate the observations for responders and assign each responder to both of the stage 2 interventions. The resulting data set now has repeated observations for some participants. That violates independence assumptions of normal linear regression, but we can address that using clustered standard errors from generalized estimating equations, or GEEs. And this is the approach recommended in that 2012 paper. And here's the code to do that. It's pretty easy. We pull out just people who are responders, and we say observation 1, first time, stage 2 is higher intensity. Then we make another one, again, just the responders. This time it's observation 2, and now we put them in the both interventions category. If they're non-responders, then we don't duplicate it at all. It's just as is. And then we just row bind, we combine all those data sets back together. So this just duplicates responders and puts them for stage 2 rather than being missing, once in the higher intensity adaptive program, once in the both intervention adaptive program. And the reason for that is we're not trying to evaluate just that final step. We're trying to evaluate that entire stepped care adaptive intervention. And that would include always both responders and non-responders. So we duplicate them to put them in both. We deal with the fact that we've sort of doubled our data by using these clustered standard errors in GEEs. They work almost like normal linear regressions, but they just adjust the standard errors a little bit, some fancier back-end calculations to take into account clustering. And now we can run a fairly normal-looking linear regression model, to be honest. We say outcome is post-intervention ISI. We've got a stage 1 intervention and a stage 2 intervention, and we include the interaction between them. So we have the main effect of stage 1, main effect of stage 2, and their interaction. That's important because whether you get higher intensity of both interventions might differ. The impact of that might differ depending whether you initially started with light or CBTI. So by including the interaction, we get both of that. We adjust for baseline ISI to covary out that baseline score. We specify our data set. Only special thing here, we need to tell this GEE GLM, generalized estimating equations, generalized linear model. We need to tell it what our weights variable is, weight, and we need to tell it the ID for participants, ID, and that ID is used for clustering. And then I summarize that result, m2.smrt, here. And this looks like a fairly standard regression equation. These coefficients, p-values, etc., would be interpreted as normal. The only thing I want to highlight here is that here, this number of clusters, 240, this should be the number of participants. Once we duplicated some participants, there's going to be extra rows in the data set. There's now 304 rows in our data set. But when you run it with the proper clustering, it should tell you there was only 240 clusters. The other thing you'd expect is that the maximum cluster size is 2, and that's because at most we duplicated the data of people who were responders. We never made 3 copies of it, so you should only have at most 2 observations per ID. So this is just sort of a sanity check that this little bit of data management worked correctly. Now, I'm not going to interpret these regression results because they're kind of hard to interpret this way in this main effects and interaction format. And then for interventions for RCTs, oftentimes we focus on the means in each of the groups and the differences in those means. So we're going to focus on those adaptive intervention. We're going to focus on the adjusted mean ISI values at post-intervention and their comparisons. And we're going to use the EM means function again to get these estimated means. These are based on the model, which is properly weighted and clustered, so the results, including the estimated means and their confidence intervals, will take all of that into account. Well, it's worth noting how to interpret each of the adaptive intervention means that we're going to see. Right? So one of them is start with light and then get the higher intensity version of that. This is the adaptive intervention where people start with self-help light for 1 month. If they respond, they continue with self-help light for another month. If they do not respond, they are given higher intensity light, which is basically problem solving and motivational interviewing to support regular light use. The EM mean is the estimated average ISI at post-intervention for people given that entire adaptive intervention program. So that is, it combines responders and non-responders who all would have taken part of that stepped care intervention program. So it's the overall what happens to people who start that adaptive intervention model. And I'll let you read on your own time the rest of these, but it just walks through very explicitly what each of these different adaptive intervention programs are. But the key part is they're adaptive. It's not just people who had a response or who had no response. It's that overall stepped care package, including responders and non-responders, and what the overall average outcome is of that. Here we use the EM means function. We give it our model and we say I want to get the means for both stage 1 and 2. And then we use the confint function to get confidence intervals for those means. And Cable gives us a nice little table for this. So here you can see these 4 different adaptive intervention programs and what their estimated adjusted post-intervention ISI mean is. We can see that if you started with light and then the adaptiveness of it was a higher intensity version of that, your estimated ISI at post is 12.5. The very lowest is people who started with CBTI, and if they did not respond to that, they subsequently got light, who have an estimated mean of 10.8, although it's very close to people who started with light, and if they didn't respond to that, they got self-help CBTI, who have an estimated mean of 10.9. 95% confidence intervals shown over here, lower confidence limit, upper confidence limit. The other thing we might want to ask, of course, the means are helpful, those often get reported, and we might want to ask whether one specific adaptive intervention program yields superior results to another. So we can see the means here, but now we might want to know, well, is this 10.8 significantly better than this 12.5? We can use the pairs function to get all possible pairwise comparisons on estimated means, saved in this object we'd already saved them in, and use the confint function to get confidence intervals. If we change confint to summary, we'll get p-values instead. By default, it'll do a 2-key adjustment for multiple comparisons, and that 2-key adjustment, if we're getting confidence interval, is an adjustment that makes the confidence intervals wider to properly take into account the multiple comparisons. If we use the summary function, that 2-key adjustment would adjust the p-values so that the p-values are taking into account multiple comparisons. And now we can see here these contrasts. So I'll just walk through 1 or 2 of these. This first one is comparing what happens, what is the average in people who start a program where they start with self-help light. If they respond, they continue with it. If they do not respond, they get that additional support in using the light. So light, higher intensity. And how is their mean different from people who started with self-help CBTI? If they respond, they continue with that. If they do not respond, they get therapist-delivered CBTI. And this is the difference. And so what we can see here, this 1.423, is that people who start with self-help light and get higher intensity if they don't respond, compared to the stepped care model of starting with CBTI and getting higher therapist-delivered CBTI if they don't respond, the light one ends up 1.423 points higher in ISI at post-intervention than does those who start with self-help CBTI and get therapist-delivered for a month if they don't respond. And that 1.423, the confidence interval limit for that does not include 0, and this is an adjusted one, right? So this has been adjusted for multiple comparisons. And so this would be a statistically significant effect, right, at 0.05, saying that basically that adaptive intervention program, that stepped care model, starting with self-help light and getting a more intense version if you don't respond, is inferior, although it's 1.4 points off, to starting with self-help CBTI and getting therapist-delivered CBTI if you don't respond. And we can sort of see here in summary, if you start with self-help CBTI, it doesn't matter whether you up the intensity to the therapist-delivered CBTI or switch over to self-help light if they don't respond, right? This difference is not significant. There's a small difference, but it's a 0.28 difference in ISI units, and these will be directly in the units of ISI. So a 0.28 point difference in ISI, pretty tiny, not significant. Confidence interval includes 0. If we wanted the specific p-values, we'd use the summary function. If you end up with both interventions, it doesn't matter what you started with. Right? If you get both interventions in the end, here, they're very, very close to each other. They're only 0.08 points off. So it doesn't matter whether you want to start with self-help light or start with self-help CBTI. As long as your people don't respond, you switch and you give them the other one. These results would say those two step care models produce equivalent, right? There's no difference in those results. Not only are they not statistically significantly different from each other, the practical difference of a 0.08 difference in ISI units is very, very small. So this really kind of gives us this summary, and it shows you how you can actually look at and all those different questions that you could potentially answer from this SMART design. Now, when we talk about a power analysis for this SMART design, which is the last thing we're going to talk about, we could be focused on any one comparison. We could be focused on all of them, right? There's a lot of different pairwise contrasts here. We also earlier had just what is the overall effect of the stage 1 intervention. We also have the choice of whether we want to power the result study for unadjusted results or results adjusted for multiple comparisons. And the adjusted for multiple comparisons would become particularly important if the primary aim of your grant was actually to look at all of those different pairwise comparisons. For the sake of example, though, suppose that although all the comparisons are going to be evaluated, the primary aim of this grant is actually just to evaluate whether an adaptive intervention, starting with self-help CBTI and adding therapist delivery if no response, is superior to starting with self-help light and adding support if no response. Therefore, we're going to use an unadjusted result because we only have one main hypothesized contrast of interest. That's our main point of this grant. The other stuff is sort of extra, maybe the secondary outcomes, secondary aims. So we're going to focus on that, and we won't have the multiple comparisons. We're going to actually pull all those other p-values anyway, so we could easily look at the power for them. If you're running a Monte Carlo study, you may as well store a lot of the p-values because most of the time is setting it up, not which p-values you store at the end. But I'm going to focus just on that one. The Monte Carlo study follows the same approach as for a standard RCT, but the SMART design is more complex with a lot more layers and a lot more groups, so we need to specify many more parameters. This will kind of show you Monte Carlo studies can quickly become quite long. That's the downside. An upside of this is each piece is often not much more complex. We might have more variables. Now we have a baseline ISI, midpoint ISI, post-ISI. But in all these cases, we're often just trying to figure out, well, what's their mean, what's their standard deviation, what are the regression coefficients that I need to plug in here. The following code's rather long, but each piece is fairly straightforward. Some parameters are fixed. With as many parameters as we potentially have in a SMART design like this, if I tried 2 to 3 options for every parameter, we would literally have thousands of different combinations. And that's going to become computationally intractable. Like, I think we might have hundreds of thousands of different combinations if I had 3 options for every single parameter that's possible here. So I'm fixing quite a few parameters and focusing on varying just 4 parameters that I might think are especially critical, or 4 parameters that I'm especially uncertain about. The first one is the sample size. We always need to vary the sample size because we don't know exactly what sample size we need for adequate power. The next one is the baseline standard deviation of ISI. And actually, in the code that I do, I'm basically using the same standard deviation for ISI at baseline, mid, and post. And so this equates to varying the amount of variability in ISI. And the 2 standard deviations I'm going to try are 3 and 4. So some variability, some more. These, in reality, would need to be based on literature in the population that you're looking at and saying, well, what's sort of that? Note that for standard deviation, generally, it's conservative to go larger. So if you think it's probably 3, a conservative estimate might be 4. It's sort of bigger. You would not go down and try a 2. Because the more variability there is, the more background variance there is, the harder it is, the less power you have to detect an effect. So if you want to sort of play it safe and you're pretty sure it's 3, but you want to be safe, you go some number bigger than 3. The other thing we're varying is how much people in the self-help CBTI condition who show no response decline from midpoint to post when given therapist-delivered CBTI. So that is, how much, for people who don't respond to self-help CBTI after the first month, how much better do they get than that sort of midpoint check when they get the therapist-delivered CBTI? Does that help them? Not at all. And so here what I'm going to try is either that therapist-delivered gains an additional 2-point decline or an additional 1-point decline in ISI. And then how different people who did not respond to self-help CBTI are post-intervention if given self-help light, both interventions, compared to therapist-delivered CBTI. So either is giving them both interventions, is that 1 point better than doing the therapist-delivered CBTI, or is that no points better? Are they equivalent? Those are the 2 that I'm trying. And just those 2 things gives us 8 different parameter combinations. excluding sample size. Trying samples of 100 to 1,000 by 20 gives us 368 conditions when including the different sample sizes exploring. Each of those 368 conditions is simulated 200 times with different random numbers, resulting in 73,600 data sets and analyses being run. On my machine, again using 24 cores, this took about 6 minutes. It should scale fairly linearly, so if you are only running this on a single CPU core, you might expect it very ballparky. This isn't the only thing that matters, obviously, but speed matters, etc. too, but I might expect it to take around 2.5 hours. Now, while this code is a lot longer, and again, if you're not interested in the code, feel free to skip over this, each piece is fairly straightforward. I have, well, what's the number of people? I'm going to do a sequence from 100 to 1,000 by 20. What's the ratio for the first randomization? What's the mean ISI at baseline? What's the standard deviation of ISI at baseline? 3 or 4. How much decline in ISI from baseline to midpoint is considered a response? What's my response cutoff? Here I'm using -4. That's needed because part of this Monte Carlo simulation needs to actually see how many people respond and how many people do not respond. Because if everybody responds and only 10% of people do not respond, then the number who get re-randomized is much smaller. So this response cutoff matters. It also matters how much you expect people to decline from baseline to midpoint in response to that first line, stage 1 intervention that they get randomized to in the CBTI condition, in the light condition. So I'm saying I expect that people who get self-help CBTI after 1 month will on average be 3 points lower than they started, whereas people who get self-help light after 1 month will be on average 2 points lower. Each of these you need to come up with and figure out and justify what those are. So all of the parameters get laid out there. These equations look a little bit complicated, but they're the way to calculate what the residual standard deviation needs to be in order to have the same overall standard deviation in ISI and all these different groups. We've got 368 different conditions. We want to have 200 replicates for each condition. Set up the cluster and set it up. And it works pretty similarly. We simulate first our baseline ISI here, which I just called X. Then our midpoint ISI in the CBT condition, which I'm calling Z. I calculate the difference between them, and then I determine whether someone's a responder or not based on whether they exceed that cutoff or not. Come up with the stage 2 randomization, number of people times the number of people who make it to stage 1 times the ratio that gets randomized in stage 2. Then I select only people, stage 2 randomization only for people who did not respond. Calculate the midpoint scores for the responders and non-responders, get the average midpoint score in each, then calculate post-ISI based on all of that information plus the parameters I had in those with no response and post-ISI in those with a response, and put that all together in a data set, and then do exactly the same thing, but this time using the parameters for those who started off with self-help light. So lots of code, but each step is fairly straightforward. Finally, we put all those together in one data set, combining the light and the CBTI data set. Better labels to our stage 1 and stage 2 groups. And then, remember, because for the Monte Carlo study, we actually need to run the final analysis. So just like I duplicated responders for the analysis, I need to duplicate them here in my Monte Carlo study, add the weight, and then literally running the final models that I ran, store the p-values. And here I've got this bigger set. Stage 1 is just that stage 1 p-value, difference between self-help CBTI and self-help light, and contrast 1 to 6 p-values. Those correspond to these 6 different contrasts here from 1, 2, 3, 4, 5, 6 that we saw in this table. And so I store out all of those p-values in a data set. I'm not doing any adjustment here. I've said adjust equals none because I don't want a multiple comparison adjustment, because for this hypothetical grant, we're really focused on this first contrast here. Run that, merge it in with the rest of our parameters so we know which condition they belong to, and save the results. As before, I saved that into a data file. You can download it here if you want to be able to play with it, but you don't want to run it on your computer for 6 minutes or 2.5 hours or however long it takes. So we can read that in and we plot the results. And it works pretty much the same way as before. Here I'm focusing on contrast 1. I actually have all the other contrasts, so if I wanted to know what our power was for any of the other pairwise contrasts under the assumptions that I made, we could just swap contrast 1 here for one of those other contrasts. And now we've got this graph. X-axis is N. The different colors are how much people change in response to how much the non-responders benefit from the therapist-delivered CBTI. Do they get 2 points better or only 1 point better? The columns are what was the baseline standard deviation for ISI, what's the variability of ISI. Is it 3-point standard deviation or 4-point standard deviation? And the two rows, which in this case don't seem to make much difference visually, is whether people who get light in addition to self-help CBTI, how much better they do than people who just get therapist-delivered CBTI in addition to the self-help. Do they do 1 point better or no points better? And that doesn't actually change our first contrast. It would change some of the other contrasts, but for the first contrast, which is what we're looking at power for here, it doesn't make much difference. So we could kind of ignore it and focus on just one of these rows. What we can see here is that for 80% power, if the standard deviation is lower, 3, we need a lot fewer people. When the standard deviation is higher at 4, we need quite a bit more people. You can see there's lower power. You can also see that it makes a big difference whether therapist-delivered CBTI helps people an additional 2 points or only an additional 1 point. If it only helps an additional 1 point, telling these two groups apart requires, again, more people. And here I'd say, well, it's going to take about 500 people in this overall SMART trial, right? 500 people to go into that initial randomization in order to have at least 80% power across all of the conditions being evaluated, right? That is the minimum number of people that allows me to be adequately powered in all conditions. If I think, well, this 4-point standard deviation for ISI is kind of too high, I think it's going to be 3, then we could lower the sample size quite a bit, maybe down to 300 or so. But this figure sort of will interpret and tell us what that is. Again, key point here, this is only telling us power for the conditions and the assumptions that we made. If ISI isn't normally distributed, if it's actually a 5-point standard deviation, not 3 or 4, then these results won't apply to that, right? We haven't studied those. We only know what the Monte Carlo study only tells us the conditions we asked it to explore. So that's pretty much it. The very last thing, I just wanted to show you a sample write-up from one of my RCTs that's just starting. This isn't from a SMART trial. It's from a 2x2 factorial RCT. And in particular, the last sentence shows a way of trying to succinctly convey complex results from a variety of conditions. All right, so I described this all out. We've had this here. Results from the power analyses revealed that randomizing 210 women will provide greater than 80% power to detect main effects of CBT and bright light therapy on an ISI and fatigue under most assumptions with an alpha of 0.05. And I detailed out what all the different assumptions I was in here. Now note, this isn't a write-up for a grant. You wouldn't have this much space in a grant. This is a write-up that I was sending to some committees, so I had a little bit more space to play, and I also was able to send them graphs. But I talk about all the different conditions I set up, and I had references in there about where I'm actually pulling these various numbers from. That's just a little bit of a sample write-up. So that's everything for the talk. Thanks so much for listening. If you've got questions, we'll be at the session on Monday and be happy to answer those.